Hello everyone, Jim Malis again. Let's talk a little bit. Let's talk about Chapter 7. Some pretty fascinating stuff that goes on with the physics, you guys, and it's a great book that we use. In the earlier video that I had done related to Chapter 6 from the Katz book, we had to correct problem number 41 from Chapter 6. Again, anybody can make a mistake, guys. It happens. I think the correction I gave is the right way to make it. It looks like the error was they had considered some quantities they did not need to consider. In fact, we're not supposed to consider. But we fixed it. So I'm going to fix it in my notes as well when we take care of it. But like I said, I also followed what they had done, and I didn't pay close enough attention to it, so I thought that they were right. I'm now confident that they were wrong, and I corrected it to the best of my ability. So that was the earlier video, Chapter 6, problem number 41. What are we doing right now? Well, we're doing Chapter 7, problems 13, 33, 59, and let's talk about it. Let's talk about gravity and things of that nature. Gravity and what we can say and some of Kepler's laws and things of that nature. So let's see exactly what we can say here, guys. We talk about, for some reason, it's simply not here. Or are they here? Yeah, they are here, actually. What am I talking about? Okay. So let's try to make this stuff make a little bit of sense to us, I guess you could say. The force of gravity, the force between two masses, let's say let's pretend there's no other forces anywhere in the universe right now, just for this one instant. And let's talk about those two masses and the force that exists between them, the force of gravity that exists between them. Well, what is the magnitude of that force and how does it work? G is a constant, the universal gravitational constant. This is the mass of mass 1, and this is the mass of mass 2. So this is the mass of object 1, this is the mass of object 2, this is a constant, and R is the distance between the two objects. R is the distance between the centers of mass of each, the center of mass of one object, the distance from the center of mass of one object to the center of mass of the other object. So from the center of mass of one object to the center of mass of the other object, that distance is R. So if it's like this, here's a mass, here's the center of mass, let's say, here's the center of mass, let's say, that's where R is. Okay? Essentially what they're trying to say here, guys, is that the force of gravitational attraction is some constant times mass, the mass of object 1, some constant times the mass of object 1 times the mass of object 2 divided by the square of the distances between them. What does this mean? That means the more massive the objects are, the bigger the product will be. If both masses are very large, the product of two very big numbers is a very big answer. So M1, M2, if it's a very, very big number, and if the distance between the objects is very small, if this is big and that's big, huge answer for the product. And if the distance between them is small, whenever you divide by something small, you get a big answer. Whenever you divide by something big, you get a small answer. So it's an inverse relationship here. If R is very small, when you square it, it's still very small. And if M1, M2, the product is very big, what's big divided by very small? Very, very large. So you get a very large gravitational force if the masses are very large and the distance between them is very small. You get a very small gravitational force if the masses are very small and the distance is very large between them. But this right here is the force of gravity. And this is just a constant right here, so it doesn't really mess things up too much. Now we've been using G, the acceleration due to gravity is about 9.81. Now remember that other video when I was trying to actually prove what the right answer was for for problem number 41, chapter 6. I use 9.81 meters per second to kind of agree with the numbers that were being proposed for at least some of the stuff that we were looking at. So G is 9.81. That's usually what this book uses. If you use 9.8, there shouldn't be too much of a problem. Should not be too much of a problem. But we've been using roughly 9.8 for G, but how do we even get that? Guys, I got a question for you. Didn't we say that the force of gravity close to the surface of the Earth, is m times G? Yeah, true. The force of gravity close to the surface of the Earth is mg. Yeah, that's just a fancy way of saying the weight. The weight of an object close to the surface of the Earth, the weight of an object close to the surface of the Earth is mg. Okay. So that's the force experienced by the mass m. The force experienced by the mass m is mg. Force experienced by the mass m is mg. The force experienced by the mass m, that's close to the surface of the Earth. It's also equal to this. Mass of the Earth, sub E, capital M we'll call the mass of the Earth, and small m we'll call the object, me, my bicycle, whatever, over r squared. And this is, I'll say r sub E. Depends how they actually want to write that. For our purposes, r sub E is the radius of the Earth. Remember, every object pulls on every other object as though it's pulling from its center of mass. The entire Earth pulls on other objects as though it is pulling from its center of mass. And it's pulling at the center of mass of some other object out there. All objects pull on one another as though they're pulling from their center of mass. Well, what's the distance between myself and planet Earth? Well, right now, there's no distance between me and the surface, but the Earth's not pulling me as though it's pulling me from the surface. The Earth is pulling me as though it's pulling me from its center, from my center, roughly here, up here somewhere, from my center down to the center of the Earth to my center, that distance is roughly the radius of the Earth. So that's the distance between me and the center of the Earth. If that's the case, those two forces are equal. F equals F, mg equals divide by small m on each side. G equals, small g equals the universal gravitational constant times the mass of the Earth over the radius of the Earth squared. That's where you get the 9.8 or the 9.81. Okay. If you actually grind the numbers, find the mass of the Earth, find the radius of the Earth, square it, find the universal gravitational constant, grind all this out, you'll get the answer, 9.8 or thereabouts. This is a rather interesting matter. The acceleration due to gravity actually changes. If you're not at the Earth's radius, but somewhere else, if you're really far away, the pull associated with gravity is going to be smaller. Let's say I go 2 Earth radii away from the center of the Earth. I'm 1 Earth radius. I am right now 1 radius of the Earth away from the center of the Earth. What if I go another Earth radius up that way? What kind of gravitational pull am I experiencing? Well, if I went twice as far away, the G in that instance, this is going to be another G, is called G prime. It's not the G we're used to. It would be, 2 Earth radii, huh? Right now, I'm only 1 Earth radius away from the center of the Earth. What if I go another Earth radius further away than what I am? That's 2 Earth radii away from the center of the Earth. Well, when you're to do something like that, you get the new G, I guess you could say, for that location is GM 4RE squared. That's 1/4 GM over RE squared. Wait a minute, GM over RE squared is the original G. The new, I don't want to say the new and improved, I mean, it's not a commercial, guys, but I mean, I would have 1/4, I would accelerate down toward the Earth initially, way up there, if I was 2 Earth radii away from the center of the Earth, rather than just 1 Earth radii away, which is what I am now, I would accelerate with 1/4 of a G. I'd accelerate with 1/4 G for that to be the case. My acceleration due to gravity would be about, about 2.45 meters per second. I would be 1/4 the weight up there. My mass would be the same, but I'd have 1/4 the weight, and I would have 1/4 the acceleration. If I jumped off a ledge up there, somehow if somebody hey, there was some kind of object there, hey, let me just jump off this thing. What am I experiencing, So I was being held before. I had a jetpack, and I turned the jetpack off. Bam, and I start falling. I'm not going to fall at 9.8 meters per second. I'm going to fall at 2.45 meters per second. 1/4 the amount for that to happen. Okay, so that's an interesting point in its own right. So let's see here. So that's okay, just something to kind of keep in mind. So what can we say here? Well, I mean, let me come right back to it. I can generally tell you what G is going to be. Your G4, the acceleration G that you can potentially experience depends upon how far away you are from the center of the Earth. So it becomes a function that way. This just happens to be the one near the surface of the Earth, and it's called the G that we're used to knowing, which is 9.8 meters per second. Okay? So that's one thing to kind of keep in mind when we're doing all this. In addition, to all that, let's say something else. We can talk about Kepler's laws of motion. I mean, we talked about Newton's laws of motion. Let's talk about Kepler's laws regarding orbital motion. He had 3 laws pertaining to that. Let's talk about them a little bit. Let's start doing some problems related to it, and let's see what we can say. Okay. Kepler's laws of planetary motion. Kepler's laws of planetary motion, better way to put it. They are as follows. They don't have to be planets either. This, for generally objects that are in space that are going around and revolving around something. There was a revolution going on. Let's see how this stuff all plays out. There's orbital motion going on. The Kepler's laws. Number 1, Kepler's first law. Kepler's first law: planetary orbits are ellipses with the sun at one focus. Usually. Well, okay. Let me say this, and let me tell you what they usually do. That's an ellipse. It looks like a circle that's been deformed a little bit. You could say, it looks like a circle that's been deformed a little bit. It looks somewhat like a circle. For our purposes, when we're doing a lot of these problems, unless they explicitly tell us otherwise, which is like almost never, at least for what we're doing right now, we're assuming circular orbits. A circle is a special kind of ellipse. I mean, the ellipse has a formula. X squared over a squared plus y squared over B squared equals 1. If A and B are equal to one another, let's say A equals B equals R, then you're looking something like this. Multiply by R squared on each side, and you get the famous equation of a circle in two-dimensional space, looking like this. A and B, if they're not equal to each other, you're going to get this ellipse. There is, let's say this is the sun, and this is, I don't know how a good way to say this. This is the sun, let's say, and let me not make it quite as dark here. That's the sun, and this is another, it's not really anything there. I'll explain in a second. This is a planet going around here. And the planet orbits the sun. If you were to go right to the center of the sun, and right to the center of the these two places, the center of this large sun and the center of this very small object, these two, that's called a focus, and that's called a focus. These are called foci. The sun, or whatever massive object it may happen to be, it may be a black hole, it may be another galaxy, it may be a white dwarf, it could be whatever it is. Whatever the planetary object is, it's at one of the whatever the planetary object is, it is at one of the foci, and the other foci is just, you kind of write this here just for the mathematics of it. But anyway, the orbits that take place for Kepler's first law, what they're basically saying is, for Kepler's first law, planetary orbits are ellipses with the sun at one focus. Okay, so let's just deal with the sun for now and our planetary system, but it could be anywhere in the universe. And it can be some other massive object and how things behave for the purposes of the discussion that we're doing. But for Kepler's first law, planetary orbits are ellipses with the sun at one focus. Well, yeah, and we usually simplify the discussion and we just pretend we're dealing with a circle. The sun's right dab in the middle, and you got, and then it goes there. A circle is a special kind of ellipse. Every circle is an ellipse. Not every ellipse is a circle. It's like me saying every Corvette is a car, but not every car is a Corvette. Same thing here. Every circle fits under the category of ellipse, but not every ellipse is a circle. That's clearly not a circle. This is not a circle, but it is an ellipse. This is a circle, and it's a special kind of ellipse called a circle. Okay. So for Kepler's first law, the orbits are going to be elliptical orbits. Planetary orbits are ellipses, and the sun is at one of the foci. 2. Kepler's second law. Kepler's second law, a line joining a planet to the sun sweeps out equal areas in equal times. All right, now, let's stay with the ellipse theme, I guess. Here's the sun, here's the other one right here. If you were to draw a line right here, and here's the planet going around it. In a time of, let's say it takes 10 years to go around maybe this planet takes 10 years to go around. Well, I'm trying to think exactly how I want to say it. It takes 10 years to go around. And let's say 2 years, this guy goes from here to here. It sweeps out this area in 2 years. When it gets over here, it sweeps out an area as big as the first situation right here, but it does it in 2 years. So it's going a lot slower here. There's a lot here. This is how far the planet went in 2 years. From here, going that way, the planet went this far in 2 years. The planet went this far in 2 years. Who's going faster? Well, that's kind of obvious. Let's say it again and come back to it. I mean, this is for Kepler's second law. A line joining a planet to the sun sweeps out equal areas in equal times. Like I said, this isn't I don't know how good this drawing is, guys. Let me make it a little bit bigger. Maybe that, I don't know how good, it's hard to say. Perhaps now I made the area too big. I don't know. Can argue this all day long, I guess. But let's go here. Let's make it a little bit bigger. All right. This area and that area are equal. They almost look like two triangles. They're not triangles. Let's not go there. But they almost look like two triangles. Here's a triangle. Here's a triangle. This one's got a broader base, but a shorter perpendicular. This one's got a shorter base, but a longer perpendicular. If I find the area of this triangle and I find the area of that triangle, they're equal. Well, they're not triangles, so let's not even go there. But let's go there, but let's remember they're not triangles. But they kind of resemble them. The area is what it is. This area right here is A1. This area right here is A2. And A1 equals A2, or any of these. For equal areas get swept out for equal periods of time. Period. Notice this guy, make this a little more fired out this way. Notice this guy isn't going as fast. He cannot be going as fast, guys. How much arc length did this guy cover? How much arc length did this guy cover? I don't know. He covered something. You want to bet this is a lot more? For the same amount of time. Which planet is going faster? The one that's closer to the sun. The one that's closer to the sun is going faster. Oh, wow, it must be doing more area. No, that arm right there ain't that long. This arm right here is very long. This area equals that area. Equal areas get swept out in equal periods of time. Equal areas get swept out, you guys, in equal areas of time. Equal areas get swept out in equal time periods. In 2 years, this guy covered all that ground. In 2 years, this guy covered all that ground. All that ground in just 2 years. In the same just 2 years, only this much ground was covered. So I guess the closer the planet is, the closer that the planet is to the sun, I'm a little short on the chalk, you guys. Let me see what I can do. I got preference for some chalk over other chalk, but that's neither here nor there. Let's get the discussion under control here. The closer the planet is, the closer that the planet is to the sun, the faster it has to go to avoid getting sucked into that situation, to avoid losing its orbit. If it's really close to the sun, it better be going very fast or else its orbit will degrade. It's going very fast here. It's got a lot of kinetic energy here. It's got less potential energy, but more kinetic energy. Here, it has more potential energy, but less kinetic energy. The energy it has in total is the same in both circumstances. There's not a lot of kinetic energy here, but a lot of potential energy. Here, there's not much potential energy, but a lot of kinetic energy. It's going faster right here, guys, than it is going right there. If it's an elliptical orbit like that. Now, again, we kind of get around this sometimes when we're doing some of these problems. We're going to make it a circular orbit. We'll talk about that in a bit. But that's something you want to talk about. For 3, they say something pretty fascinating. For number 3, for Kepler's law number 3, if period capital T is measured in years and the semi-major axis A is measured in astronomical units, AU, Kepler's third law is expressed mathematically as T in years equals A to the third in astronomical units. The general form of Kepler's third law is as follows. Okay, we're going to write it down, and then we're going to back up and do a little bit of work on that. They're saying this guy right here in years is equal to A, the length of the semi-major axis A is measured to be this. So gets a little bit on the wacky side here in astronomical units. They're saying this. They're saying you can express that as this right here, I guess you could say. This gets expressed roughly like this. It's not as difficult as it looks. It's much more manageable than one might think. This right here is identical to this right here. Well, you say, hey, it sure doesn't look like it. Constants don't create a lot of problem, guys. M is the mass of the sun. What sun are you talking about? Our sun. Our sun. But it could be another sun that's, I don't want to, it could be another sun or another object that is 10,000 times, it could be another sun that is 10,000 times more massive than our sun somewhere else in our galaxy or somewhere else in some other galaxy. There is a sun with mass 100,000 times the mass of our sun. This could be a sun right here which is 100,000 times more massive than our sun, or a black hole, or a black hole or white dwarf or something like that, and its mass could be 100,000 times more than the mass of the sun. Using our sun, that's fine too, or using another sun, 100,000 times more massive than this, or some other object, 1,000,000 times more massive than our sun. G is the universal gravitational constant. That doesn't change. 4 is 4. It doesn't change. Pi squared is pi squared. That doesn't change. This could change depending where you are in the universe. This thing right here could change depending upon where you are in the universe. They're basically saying, and here it's weird how they do this. Guys, I already told you I think I've already told you this. I know I've already told you this. Maybe I haven't done it well enough, but let's kind of go back there again. Units of measure are kind of arbitrary. I can make up my own angular units, right? I can make up a lot of angular units. I can make up a lot of units for mass, for weight, for length. I can call this length the gym unit. You know what I mean? It's the gym unit is actually equivalent to 1,000 meters. Well, that's called a kilometer. Let me be more innovative. The gym unit is equal to 1,500 kilometers. We'll call it 1J. 1J is equal to 1.5 kilometers. So it's equal to 1,500. 1J is 1J is equal to 1,500 meters, 1.5 kilometers. You can make up anything you want, guys. They got it set up in such a way that an astronomical unit is the distance from the sun to the earth. The average distance from center to center. From the sun, center of the sun to the center of the earth, that's one astronomical unit. On average. A is, so the number of astronomical units, that would be. What's 1 foot? 12 inches. What's 1 meter? 100 centimeters. What's 1 centimeter? 10 millimeters. They got to have a unit. Well, here's a unit for you. One astronomical unit is the distance from the sun, our sun. One astronomical unit is the distance from our sun to our earth. The distance from the sun to the earth is one astronomical unit. This thing called Earth goes around the sun one time in one unit of time measure. That unit of time measure is called a year. So this is the time in years squared equals the number of astronomical units away something is cubed. What does that mean? Well, it means a lot. If we're talking about the planet Pluto, which is many astronomical units away, see, our Earth is only one astronomical unit away from the sun, but some other planet might be 20 astronomical units away from the sun. If it's 20 astronomical units away, that's a big number. Yeah, that means the time is going to be a big. Generally speaking, if it's far away from somewhere, if we're in the same star system, if we're in, wherever it is, anywhere in the universe, we could be in the galaxy, some galaxy far away, in a galaxy far away, and the sun could be much, much more massive in that galaxy. There's somewhere in that galaxy, there's a solar system where the sun is 100,000 times more massive than our sun. 100,000 times more massive than our sun. And there, let me compare what goes on with the planets in that other star system in another galaxy. Yeah, I can compare those to each other. And I can compare what happens in our star system, in our solar system, in our galaxy. If we're going to compare what happens between the two, we got to do a little more math. But within a particular star system, this works. It is a relative phenomenon, you guys. Let's say they're not using astronomical units. Let's say they're using... Let's say they're not using astronomical units. They're using some other unit. You know, the Einstein unit or something. You know, what's that? Well, an Einstein unit's, every Einstein unit, we'll make one up. Every Einstein unit is 5 astronomical units. Okay, that's my new one. It's not the 1 astronomical unit, it's 1 Einstein unit, which is 5 times bigger, which is 5 times the size of the astronomical unit. And then the time here, we'll call it an Einstein time. So one's an E for Einstein unit, or EU, or whatever, and the other one's the ET, Einstein time unit, and that's 10 years. Every single Einstein time unit, ETU, is 10 years. It doesn't matter, guys. Agree on the units, and this stuff is a comparative phenomenon when you do things like this. In my practice exams that I was giving before the COVID crisis hit, there's all these practice exams where I'm showing how to actually compare things. I'm asking certain questions on that. Well, down the road, maybe that resolves and we can start asking more questions like that, pencil and paper, on some of the exams. But for right now, let's take a look at what we have. And I'm saying this works. This right here is just a constant. Don't let it bother you too much. They can figure this out. The constant right here doesn't change a thing. The big time reality, ladies and gentlemen, is right here. The period, the square of the period, for this one right here, the square of the period is directly proportional to the cube of the length of the semi-major axis. What's this semi-major axis? Here's a focus. Here's a focus. From between the two foci all the way to the edge, the long way right here, that's the semi-major axis. The semi-minor axis is from the center to here, and that's B. That's the semi-minor axis, but this is the semi-major axis right there. Well, let's take a look at 3. Let's prove something. Let's prove it. Let's prove it, and then let's do some problems, and we'll kind of just take it from there. The big thing, guys, I think maybe when I erase all this, maybe it'll really make some sense, or at least drive the point home somewhat. The big thing is, the further away you are, if you're in a particular planetary system, you can compare how the planets are all orbiting within that system according to that formula. If you want to go across to some other galaxy, some other solar system where there's a bigger star, you can compare those planets within that system way over there, somewhere else in the universe. You can compare them with each other, and you can compare these planets in our solar system with each other. But to go across that, there's other stuff you got to do. You got to be aware of the mathematics that I had earlier. You can't just directly go through it. The comparison is still there, but you got to be a little more, a little deeper in your work when you do something like that. T squared is directly proportional to A cubed. In any planetary system, if one of the guys is 2 times further away, then A cubed is going to be a number 2 times 2 times 2, 2 to the third. It's going to be 8 times bigger number. The square root of, to get something here, I don't want to say this. I can say it, but I don't know how much I'm going to help people. Basically, if you're very far away within any planetary system, if you're very far away in orbit, it takes a long time. If you're really close, it doesn't take a long time. And it works according to that proportion right there. Well, let's take a look at it. Let's see if we can get some kind of a gut feeling as to why that's actually happening that way. Well, we already said you can kind of make, let's take a bird's eye view of what's going on here. That's a circle, or close to it. Well, as unusual as it may seem, I might have drawn that halfway decently. So this guy right here, from the center to here, and this guy goes around, I'd like to find out what the period is of this thing. How long does it take for this whole thing to come all the way around and come back there? You know, how long does it take for the whole thing to go all the way around and come back? Okay? Well, that's A. Yeah, it's also R. We'll say that A, the semi-major axis, is the same as the radius R. Now, got to find the period here. What's going on here? Well, it's going at a constant speed. Let's just say it's going at a constant speed, V. And there's a lot going on here. Well, I got to ask you a couple questions. You got to pretend there's a rope from here, from the sun, mass capital M, to the small mass right here, small m, mass capital M, mass small m. There's a rope right here. There's a rope right here, and this whirls around, and I want to know what's going on. Tell you what I'm going to do. This guy's whipping around. There is the force centripetal, and there's the force of gravity. What's going on? Well, the centripetal acceleration is V squared over R. So make sure I'm using like the same kind of letters they're using here. They use A at the end of it, and we get that. I say, well, A and R are the same thing. So let's just work with circles right now. Let's work with circles. A and R are the same thing. V squared R isn't force equal, look, we already know, isn't force equal to mass times acceleration. The acceleration due to the centripetal acceleration is V squared over R. And that small mass right here, and this is the large one, so large mass there, small mass here, mv squared over r. That is the centripetal force. Later on, there's this thing, there's this made up force that they use. It's really good mathematically. I'll talk to you about it when I talk about this thing called they kind of call it the suitcase problem. I've already have it solved for you in the notes, but I like to try. I'm going to do my best to do it live eventually, or somewhat live here on tape, I guess. At least for now, on tape for now, and then hopefully when this is all over, do it again. Maybe not for your class, some other class by the time that comes, if I'm still here doing this kind of work. So you guys are great to be working hard. Everybody looking at this, I appreciate the fact that you're looking at this. It means you got a great attitude, you're working hard on this stuff. And the people don't have a chance to look at this, I'm sure they're working hard too. You only have so much time sometimes, you guys. So what's the deal? There's this made up force called the centrifugal force. And that's as though that's as though there's this tendency to fly outward. It's also equal to mv squared over r. Let's not go there right now, but remember I just said that. The centrifugal force. It's where the word centrifuge comes from. Okay, we'll talk. It's made up. The one that really matters is the force that holds it in there. There's got to be a rope. When your car takes a sharp turn, there has to be a rope holding the car, helping the car make a sharp turn. It's called friction. It's called the tires on the road having friction. And that's how it's able to make the sharp. So what's holding it there is the friction. The rope holding this one here is called gravity. Gravity is the rope. And how strong is that rope? The centrifugal force, the centripetal force, center-seeking, the center-seeking force right here, pulling it inward, is F sub c. And it's got to be mv squared over r. If you want to do the centrifugal force, the made-up one, I sometimes like it because mathematically it kind of gives you a gut feeling. So if you're whipping this thing around really, really fast, this thing wants to fly off with a tendency of mv squared over r. There's like an arrow sort of going that way, wanting to make this thing fly out at mv squared over r. What's holding it? He really wants to fly out this way at mv squared over r. Yeah, what's holding it there? How about G, capital M, small m, over r squared? That's what's holding it there. That's what's holding it there. This guy, as it's whipping around, wants to fly out of orbit. Just like if I'm not wearing my seatbelt, and if there's no car door, and I'm not wearing a seatbelt, somebody takes a sharp turn, my tendency relative to the car is fly out of the car. How strong is that tendency? In terms of force? Oh, my mass times v squared over r is my tendency to fly off. It's a made-up force, but relative to the car, it's pretty real. You better have your seatbelt on. You better have a strong door. So this has a tendency to want to fly off this way, fly out of orbit. That's mv squared over r is the tendency. Centrifugal force. Centrifugal force, to fly off. Force of gravity is the rope holding onto it. That's made up, but it makes for some pretty convenient mathematics. So it's not a bad way to look at it. I'll talk more about that in the suitcase problem, one way or another. But for our purposes, that'd be centrifugal force. If you want to call it centripetal, and that's the real force, that's the force pulling this way. The centrifugal force has to be, the rope has to be how strong? The rope has to be how strong? mv squared over r pulling this way. That's how strong the rope's got to be. Okay, yeah, the rope's gravity. Set them equal like that. Okay. So, look at that. Let me see if I can do anything about it. Let me divide by small m on each side and multiply by r on each side. Let me divide by small m on each side. Let me divide by small m on each side. So this and this cancel. Divide by small m on each side and multiply by r on each side. Okay. Yeah, it looks good to me. I divided by small m on each side, multiplied by r on each side. I got that. May I ask you some more questions? Is the average velocity, you guys, the circumference, which happens to be 2 pi r, divided by the period? We've seen this argument before already. We saw that in the last video. Velocity is circumference divided by the time it takes to go the circumference. The time it takes to go the circumference is called the period, capital T. The circumference is 2 pi r. you're going to travel all the way around the orbit, which is 2 pi r, and you're going to divide it by the time it takes to get around the orbit. Multiply by, again, as I just said, you're going to find out what the circumference of the orbit is. The circumference of the orbit divided by the time it takes to go through that orbit. Distance divided by time is velocity. So what do we got? Well, we did some math. We got to here. Let's keep talking. V is 2 pi r over capital T. Let's square it. 4 pi squared r squared over t squared equals gm over r. I'm going to solve for t. Okay, we played a bunch of ways here. How do you want to solve for t, guys? I'll tell you what I'm going to do. Let me multiply by t squared on each side. There's a whole bunch of ways you can go here. Let me multiply by t squared on each side, and then multiply by r over gm on each side. So I'm going to multiply by t squared. I'm going to multiply by t squared on each side, and then I'm going to multiply by t squared on each side, and then I'm going to multiply by t squared on each side, and then multiply by the reciprocal of gm over r, which is going to be r over gm. Well, what is that now? R times r squared is r cubed. T squared is this. T squared is 4 pi squared over gm times r cubed. R times r is r cubed. Did we say r was equal to a? That's where they're getting this, guys. That's where they were getting that t cubed was directly proportional to a cubed. I'm sorry, that t squared is directly proportional to a cubed. Look at it. The r and the a are the same. We just went with the circular orbit to kind of make things more manageable. But that's the reality of what's happening, guys. Great problem. Pretty neat proof, the way they go about it. And that gets us there. All of that gets us there. All right, so good stuff to look at. Let's look at problems 13, 33, and 59 and see, is that 59? Yeah, it's 59. So let me see here. 13, 33, and 59. Okay, so we should be pretty good. All right, so let's see what we can say here. We're going to use this last conclusion to help us do number 13. Let's talk about it. Problem number 13, chapter 7, the Katz book. Problem number 13, chapter 7. A massive black hole is believed to exist at the center of our galaxy and most other spiral galaxies. Since the 1990s, astronomers have been tracking the motions of several dozen stars in rapid motion around the center. Their motions give a clue to the size of this black hole. A, one of these stars is believed to be in an approximately circular orbit with a radius of 1.5 times 10 to the 3 astronomical units. 1.5 times 10 to the 3 astronomical units, roughly circular orbit, 1.5 times 10 to the 3 astronomical units means 1,500. 1.5 times 10 to the 3 is 1,500 astronomical units. 1,500 times the distance from the Earth to the Sun. 1,500 times longer than that is the radius of its orbit around at the center of our galaxy. And it has a period of approximately 30 years. I mean, that far away, man, that thing is unbelievable. That's not a long time. 30 years to be going around, 30 years to go all the way around. Say, well, that's a lot longer. That's 30 times longer than our Earth takes to go around the sun. Earth takes 1 year. 30 years, yeah, I know. But this planet's in a radius 1,500 times longer than ours. Use these numbers to determine the mass of the black hole around which the star is orbiting. The mass of the black hole, you guys, is this guy. I told you this mass is an arbitrary thing. This guy right here is the mass that they're talking about in this case. You're solving for it here when you got all the data. That's not the mass of the Earth. That's not the mass of it could be the mass of the Earth. If I'm talking about the moon, how it orbits the Earth, how the moon orbits the Earth, then capital M would be the mass of our Earth. If I'm talking about the Earth going around the sun, then capital M would be the mass of the sun. If I talked about how something else is going around the center of the galaxy, the M, the capital M, is the center of our galaxy, or the center of that black hole, which is at the center of our galaxy. The center of that black hole. Okay? So that's something to be looking at. Use these numbers to determine the mass of the black hole around which the star is orbiting. Okay? That's A. B, what is the speed of this star? And how does it compare with the speed of the Earth in its orbit? How does it compare with the speed of light? Okay. Rather fascinating problem, you know? No doubt. So let's take a look at it. Let's see what we got here. So for 13, well, I run through the proof again for 13 in the notes. You can look at it again if you wish. For our purposes, I run through it and I do some other stuff, I guess, with it as well. But we're basically, let's see exactly here. Let me say, I don't want to do anything real careless here because it's easy to do something careless. We got t squared equals 4 pi squared over gm, a cubed. A cubed. Well, that's the radius. We just said that's the radius. We kind of made them equivalent. It's a roughly circular orbit. It's good enough for me. We got this right here. We want to find the mass. Solve for m. Multiply by m on each side, and then divide by t squared. the mass of the black hole and there's a lot to do here. Let me just see what I did. It's a lot to go here. There's an easier, I don't know if it's easier, but maybe it's a little more intuitive, you guys. 4 pi squared over g is r cubed over t squared. Why did I do that? 4 is a constant, pi squared is a constant, g is a constant. These can vary a little bit. What is going on here? Well, this is fascinating. If, in terms of the Earth and the Sun and astronomical units are concerned, if it was the Earth and the Sun that we were talking about, the radius would be 1 astronomical unit. It would be 1. 1 astronomical unit cubed is 1. 1 astronomical unit. The time would be 1 year. 1 squared is 1. 1 cubed is 1. This would be indicative of the mass of the sun. The black hole is a different dynamic. This ain't 1. R is not 1. R is not 1. It's 1,500. It's 1,500. 1,500 cubed is 1,500 times 1,500 times 1,500, which is there's a number of ways you could do it. Let me just try to think for a second here. It'd be 27 over 8. It would be 3.37, about like 3.375. It would be 1,500 would be, if you took 1,500 and cubed it, 0.3. There's a trick to this. Let me just not make a mistake using the trick, I guess you could say. It'd be 27 over 8. That'd be 3/8. Yeah, it'd be this right there, and then there'd be to the 9th. What am I talking about? Not the 9th. Yeah, 3rd, 6th, 9th. Yeah, it sure ain't 1. It's 3.3. It's 3.375 times 10 to the 9th times bigger. And the t that they're talking about is 30 years. If you square 30 years, it's 900. So it becomes 3.375 times 10 to the 9th divided by 9 times 10 to the 2nd. 9 minus 2 is 10 to the 7th. This goes into here. 1.25 times divided by 3. Let me just try to, I'm just doing some stuff in my head right here, guys. 9/8 divided by 3 is 3/8. Should be coming out to that. Let me kind of think about it, if you don't mind. No, I think it's right on the money, guys, when we actually do something like that. It's going to be 6.675. Yeah, it looks, yeah, I think it's right. So it's something like that right there. And when you actually do this, 3.75 times 10 to the 6th. Wow. Between 3 and 4 million times the mass. Between 3, what it comes out to when you actually do it, it's between 3 and 4 million times the mass that black hole has than what was earlier. That's something. So this is how many times more? This right here is one mass of the sun. It's this many times more the mass of the sun. Now the Earth, that many times more massive. This guy right here is one mass of the sun. This ratio was 3.75 times 10 to the 6th. 3.75 times 10 to the 6th, 3.75 million times more massive. Now, I kind of went a different path than what I initially showed it, but that's all right. Nothing wrong with that either. Mass of the sun, 1.9891 times 10 to the 30th. 1.9891 times 10 to the 30th. Okay, so 1. See what we got here. We got 3.75 times 1.9891 times 10 to the 36. Yeah, for real. It goes about there. It's going to be a little bit different than the answer I gave. That's all right, though. Forgive me, guys. I'm going a little different when I show in the notes, but I'm going to show you the same answer as what I go in the notes. 7.459 or 7.4, it's going to come out about 7.46 times 10 to the 36. I think the way I got it, they rounded it to just two places, 7.5 times 10 to the 36 kilograms. That doesn't, I don't know, I'm not trying to belittle the whole thing. This don't mean a whole lot. What means a whole lot is this, right here. 3.75 million times more massive than the sun is this black hole. 3,750,000. 3,750,000 times the mass. The mass of what the mass the mass of the black hole is 3,750,000 times 3,750,000 times the mass of the sun. Between 3 and 4 million times the mass of the sun is what the mass of that black hole is. You could have done this, guys. You could have done this. Said, Malus, this is great what you're doing here, but you could have gone 4 times pi squared divided by g, after you look up g, 4 times pi squared divided by g times 1,500 to the third divided by 30 to the second, and it would have spit out this answer at the end, you guys. 7.5 or thereabouts, 7.5 times 10 to the 36 kilograms. I chose to do it differently. I said, man, I'll tell you what, let me call this, which is really what it is, believe it or not. Let me call this, the way they set up the units, the way the units are set up, let me call this the mass of the sun. This right here, this ratio is 3.75 times 10 to the 6th times the mass of the sun will give you the mass of the black hole at the center of our galaxy. The mass of the black hole at the center of our galaxy is 3,750,000 times the mass of the sun. And this got me there. I just had to look up the mass of the sun and then go that way. Or I could have just ground this whole thing out right here and got it to here. But so 7.46 times 10 to the 36 kilograms, about 7.5 times 10 to the 36 kilograms. But now let us take a more simplistic look using basic ratios and proportions. So that's essentially I I had done the same thing. The numbers were a little bit different here. I show it here. The black hole is about 3.77 times 10 to the 6 times more massive than our sun. And I kind of go into that a little bit. You'll see it in my notes. This is pretty close. Right, not there, all the way to here. This is close. I came to the conclusion 3.77 times 10 to the 6th. 3.75 times 10 to the 6 is better. But I looked at some of the numbers here, guys. It depends on the numbers that you're actually using to do this. I took Dr. Katz's number, which was on the high side, and I divided 7.5 times 10 to the 36 by 1.9891 times 10 to the 30th. I assumed Dr. Katz's number was right. Very, very accurate. I divided it by this, and I got, it came out to 3 million, instead of 3,750,000 times the size of our Earth is what that black hole is. We got 3,770,000 times the size of that times the Earth. The Earth's mass is the size of the black hole. That's not a big deal, guys. Either way works fine. That is remarkable. Let's confirm that with some basic math, and I kick it around a little bit, and that's where we get the 3.75. So, what is going on here? Well, they talk about B. What is the speed of this star, and how does it compare with the speed of the Earth in its orbit? How does it compare with the speed of light? Okay, shouldn't be too bad. I got an easy way to kind of compare the two. How fast is it going? How fast is any circular orbit, guys, other than this? What does the Earth do? In 1 year, it goes around a circle. What does the Earth do? In this unit of time we call 1 year. In this unit of time called 1 year, we can make up anything we want. Language is largely arbitrary. But we got to be consistent with it, though. In this unit of time that we call 1 year, the Earth goes around a circle of radius 1 astronomical unit. Oh yeah, the distance we call 1 astronomical unit, also made up. A circle with a radius of 1 astronomical unit. The Earth going around a circle with a radius of 1 astronomical unit takes this time unit called 1 year to get it all the way around it. The Earth goes around the sun, and the sun and the Earth are part of a circle that has a radius of 1 astronomical unit. The sun goes around a circle with a radius of 1 astronomical unit. It goes around the entire circumference of a circle whose radius is 1 astronomical unit. It does that in 1 year. Does that in 1 year. Great. How long will the other one take? Well, if it does it in 1 year, it's going pretty fast. We'll say it's going speed v. How fast is that? I don't know. Because I can find out what the astronomical unit is, its length. 2 times pi times the length of an astronomical unit is the circumference, divided by 1 year. I can maybe convert years to seconds, divide seconds into meters, and find out what's going on. I got a gut feeling here. Isn't that planet or object or whatever it is, isn't one of those stars, one of those stars that is going around the black hole is 1,500 times further away from that black hole as the Earth is from the sun. 1,500 times the distance is that star from the black hole when compared to the distance of the Earth from the sun. 1,500 times the distance. That means the circumference is 1,500 times bigger. Yeah, but hey, they gave him 30 years. So what? 1,500 divided by 30 is 50. 1,500 divided by 30 is 50. That star is moving 50 times faster than the Earth. Let's find out. It's all about proportions, guys. I didn't really give an answer, but I gave a proportion answer, which is maybe just like when I was saying, 3.75 times 10 to the sixth. The black hole has a mass 3.75 times 10 to the sixth times that of Earth's mass. That's easier. 3,750,000 times the mass of the Earth is what the mass of that black hole was in part A of problem 13. How fast is the planet going? You realize they'd be going to dead heat if the planet, if that star, which is 1,500, which has a radius 1,500 times that of Earth, therefore that star is going 1,500 times more distance than the Earth is. 1,500 times the distance that the Earth is going is what that star is going. Yeah, if it took 1,500 times more time, they'd be going the same speed. It'd be 1,500 divided by 1,500. Oh, that's 1-to-1 ratio. Just like, just like what would happen with, the Earth. The Earth does one of those, and over a period of time called 1 over 1. One whole circumference associated with the Earth's orbit is 1. One whole circumference associated with the Earth's orbit is 1. One time period called 1 year is 1. Speed of the Earth is 1. What's the speed of the black hole? It's going 1,500 times more. It's going 1,500 circumferences that the Earth is doing because the radius is 1,500 times bigger. Well, if it was going 1,500 times years, it'd be 1-to-1. And it'd be the same speed. It'd be VE. V black hole would be equal to VE. Sure it would. Yeah, but that ain't what happened. That's not what happened. That's what I was trying to say earlier. That's what I'm going to try to say throughout this class. 30 units. This divided by that is 50. 50, huh? This guy was 1. V black hole is 50 of those ones. Is 50 of those Earths. The black hole is going, the star associated with the black hole. V associated with the black hole. I'm not saying the black hole's moving. That's moving too, I'm sure. But for the star associated with the black hole, man, this is more important than any kind of these numbers. Don't forget, this is 9.695698.5, whatever, 9.6958 times 10 to the 40th. If you can get an idea how fast something's going compared to something else, how much more massive this is compared to something else, how much more force, how much more energy, how much more just about anything. It is about ratios. Mathematics is all about comparison with other quantities. And this is a good comparison, guys. The star associated with the black hole, and I call it, V star associated with the black hole. Star associated with the black hole. 50 times. Velocity of the star associated with the black hole. 50 times the velocity. That's more, in some ways, that's even more important. In some regards. It's all about comparison. Practically everything we see in mathematics, engineering, physics, there's got to be a comparison. There's got to be a comparison. It's very important. Well, how fast is it going? Well, we've already kind of gone there. Let's see what we can say here. Well, okay. This thing called 1 1 astronomical unit. There's a lot of ones. There's 1 foot, 1 meter, 1 mile, 1 kilometer. You got to agree on a 1. Everything's about comparing it to the number 1. That distance between 0 and 1 is the measuring stick of everything that I know of, at least, in my limited knowledge, of everything that you do in mathematics and physics. The measuring stick from 0 to 1 is, that distance from 0 to 1 is 1. From there I can develop the imaginary numbers, the negative numbers, the complex numbers. From there I can compare quantities. Very big thing. AU is and there are a number of ways to proceed, as I say here. How fast is this thing going? Well, okay, let's just do it. 2 pi r over t. Here we go. 2 pi is 2 pi. This is that's meters. Now, let's see exactly what we're trying to do here. Are we comparing this to Earth? Yeah, okay, whatever. We can and cannot, it doesn't matter. I think on this one I went right off the bat and went for the big one here, guys, the star around the black hole. So let's see what's going on here. The star going around that. We will say 2 pi is 2 pi. The radius is 1.5 times 10 to the third. That is how many times more radius the black hole system has compared to our sun system, our star system, times 1.5 times 10 to the 11th. Forgive me. No, forgive. $30 each year, 3.16 times 10 to the 7 seconds. Per year. Per year. This thing's moving. The star associated with the black hole is really moving. 1.5 times 10 to the 6th. Hey, didn't I tell you it's going 50 times fast? I told you it was going 50 times faster. I told you it's going 50 times faster than what our Earth goes. Divide by 50 in here. 0.06 times 10. This is the star associated with the black hole. The Earth, 50 times less than that. Let me think about it. 0.3. It's going 50 times less than that. So if you multiply that by 5, 0.03 rather, 50, right? Right. 0.03. That's this guy. That's this guy. This VE. This is not exactly slow, you guys. This ain't exactly slow. This thing's going 30 kilometers per second. Our Earth is going 30 kilometers per second going around the sun. that other planet 30 kilometers per second going around our sun is what our Earth is doing. That star around the black hole system is going not 30 kilometers per second, it's going 1,500 kilometers per second. And I go into this. I talk about it's going 15 times fast. It's going 50 times faster. I already kind of showed that earlier, and I give some of the work in here as well. How fast is this star going in relation to the speed of light? Man, to make no doubt here, man, this isn't a joke. I mean, this is this times 10 to the 8th. The black hole, the star around the black hole system is going 1/200th the speed of light. One 200th the speed of light. If you want to compare these two, ratios that. And again, you can plug in the numbers the other way, go a little more, but I've given it in pretty strong detail for how this would work for 13A and B. But this is B. How does it compare, and how does it compare to the sun, the Earth? If you want to compare the Earth, you put, instead of 15 times 10 to the third, you put a 1 right here. Instead of 30 years, you put 1 year. At the end of the day, that's the Earth is going 50 times less speed. 50 times. The Earth is going 1/50th the speed of the star in the black hole system. Okay, so that's that. 33. That's 13. Okay. If you thought 13 was a mess, so is 33, but it's not that bad. The stuff's not bad. I mean, to explain this to yourself is easier than having somebody else explain it to you sometimes. You just got to make the logic work for you. If you can do a lot of this in your head and you're comfortable with what you're doing, then go for it. But make sure you're getting the right answers. If anything, kind of stay old school. Write the stuff down a lot. You can always catch yourself if a mistake is made. Okay? But that was 13A and B. Let's take a look at 33. 33 is saying 3 particles, each with mass m, are located at coordinates 0, L, L, 0, and L, L, as shown in figure 7.33. What are the magnitude and direction of the gravitational field at the origin due to the 3 particles? So the gravitational field is just force divided by the mass that would be present if it was actually there. So let's actually write that out. Let's see how we want to actually say that. So basically, guys, what they're trying to say is each with mass m, how this is going to work out. We're going to exploit the symmetry of the situation and see what we can say about it. All right, guys, there's squares and triangles all over the place, I guess you could say. I want to see what happens here to this particle, to this mass M, some mass, what the gravitational field is going to be. There's going to be a pull this way. Well, first of all, there's going to be a pull this way. There's a field that way. There's an equal field that way. Hey, wait a minute. If they pull like that, they just go right down the middle. That's kind of good because that guy goes right down the middle as well. So there's a third guy, not quite as strong, even though they all got mass M. Even they all got mass M, this guy's not getting pulled as hard. Why is he not getting pulled as hard? Because that guy's further away. But these two guys all end up going there. That's pretty interesting. Because of the symmetry of the situation, that's a 45-degree angle. That's a 45-degree angle. There are three pulls, I guess you could say, and they're all going to go right down the middle. They're going to be right down the middle. Because of the symmetry of the situation, we luck out that way. Well, they're telling us the distance is L. Let us see here. L, yeah, right. That's L. So L square root of 2 here, L here, and L here. Okay. Cosine of theta equals the sine of theta in this case, equals 1 over the square root of 2. Equals L over L square root of 2 equals 1 over the square root of 2 equals 0.707 roughly. That implies that theta is a 45-degree angle. Well, it's a bit redundant, I guess you could say. If we figure out what the pulls are, we figure out what we're doing here. Because of the symmetry here, we kind of jump to the chase, I guess you could say. There's a lot. My notes in here for the 209 people. My notes are good. Let me not replicate them 100%. Let me jump to something. There's a number of ways to do this actually, and I show the number of ways to look at it. Let's just do this. Let's say something here, guys. There is. It's hard to kind of call exactly how it's going to play out, guys. You could take this guy right here and project them right there. So you got something like that. You could take this guy right here and project them right there, and you got another wherever they are. They're somewhere here, somewhere here. So I could project this, I could take this guy and project him right here. And I could take the other guy and project them right here. Take him, project him here. Take him, project him onto here. Take him, project him onto here. Have this guy go that way and have this guy go this way. These two guys cancel, and it's only the contribution going that way. So just add those together. If that's the case, one second, please. All right, guys. Sorry about that. I had to pause for a second. I had to take care of something. So that's the big thing, guys. There is essentially, there's essentially, something like this. There's that right here. I almost don't want to put something here, but just put something here. You got something doing this. You got something doing that. You got another guy pulling this way. But man, if you resolve this guy and resolve him here, and resolve this guy and resolve him there, this guy is here. This guy is also here. This guy's going that way. I mean, there's a bunch of pulls here. If you got this guy pulling this way, you can resolve it like this and then like that. The other guy going this way, you can also resolve it right here. And then there's this guy going that way. Well, that right there and this right here and this right here cancel, and you're just talking about these two making the contribution. Okay? So that's essentially it. I mean, you had this, you can resolve it right here. And there is something doing that. All right, well, keep that in mind. There's another guy right here. You can also resolve it right here and then resolve this guy going that way. Well, this guy and this guy are equal and oppositely directed. They're gone. And it's just this that makes the contribution. So cosine 45, find what the field is for this guy, multiply by the cosine of 45 degrees, and you got that projection. Find the exact same number here, multiply by the cosine of 45 degrees, find the exact same projection, but for another situation, but it's the exact same numbers. And then find this guy right here, and then just add them. Straight out add them, and they're all going at a 45-degree angle. So if that's the case, you could basically say the field, magnetic field, somebody's call it, I think they call it G as well. This is such a charged statement because we're so used to the 9.8. But it could be anything. It's kind of a charged statement, though. Kind of a very loaded statement in a sense. We can just say this. We kind of just jump to the chase. I mean, you can look at my notes for more of the foundation for it, guys, but I think we're okay. I think we're doing pretty good. We will essentially, just trying to find out how I want to say it. You are basically saying that you got this guy right here making the pull from this far away. So it's GM over R squared, and there's your R. So you got the guy on the way top, GM, see the G field, the F is this, M1, M2 over R squared. The G field is F vector divided by some M. Which one's going to be the M? It doesn't really matter. Call this guy, call this guy M, big M, small m. Divide by that, you got G M over R squared. That's the field. The field means this, and that's what comes from that. This guy's generating a field, which is L square root of 2. That's the middle guy. That's this guy right here. The other guys are GM over, now be careful here. This guy potentially pulls anybody along this diagonal. These guys can be resolved. Remember what we said. You got this. You can resolve it to this. You got the other guy. You can also resolve it to that. This guy can be brought to here. This guy can be brought over there. This guy can be brought over here. Then there's this guy, there's this guy. Well, these guys go. They cancel out. So this guy went over here, and this guy went over here, and it works via the cosine of theta, cosine 45 degrees. The cosine of 45 degrees is 1 over the square root of 2. So one guy is GM over L squared times the cosine of 45 degrees. The other guy is GM That's all that it is. So what do we got? We got is this. Guys, I know this is about the 8th time I've said this, but this guy right here, this guy right here, you can project him with the cosine function onto the diagonal. This guy right here, you can also project him onto the diagonal as well with the cosine function. Both are projected onto the diagonal. This guy already is the diagonal. Everybody's on the diagonal. Hey, what about the outside stuff? This guy was going this way, that guy was that way. I projected this guy this way, but there's a component going up. I projected this guy also this way, and there's a component going down. The down component, the sideways down component, the diagonal down component and diagonal up component, they cancel. Everybody's diagonal. You projected this bottom guy to here. You projected this side guy also to here. This projection and this projection cancel. All you got is everything diagonal. So what's going on here? Add them together. Okay. Then what? Yeah, that's true. 1 over the square root of 2 plus 1 over the square root of 2 is 2 over the square root of 2. Square root of 2 goes into 2, square root of 2 times. Bam. That's the big one. That's the move to make. Fully diagonal. Not that bad. I mean, the notes are, the notes are easier to read than listening to me. Listening to me is never easy for anybody in my family, it seems. But anyway, and I shouldn't, probably not easy for anybody, I guess. But the notes are probably going to be a lot easier to read than some of the discussion that's there. The discussion hopefully can augment what you're doing as well. I mean, obviously we're trying to be talking as much as we can to give you some insight. You can always go one or the other. Sometimes the talking is going to help. Sometimes the notes are going to help more. Sometimes the talking is going to help more. It's hard to call it. So you just try to put it out there, and hopefully it's to everyone's benefit. You do have the fast forward button, and you do have the reverse button. So you can always look at this stuff. So this was what it is. The resultant G field is GM over L squared. Maybe, hopefully this is easy. I don't know what, it should be visible pretty good. At an angle theta equals 45 degrees. So that's it, guys. At the end of all that, this is it. Okay. Let's see what else we can say. Let's go to 59. Again, guys, despite despite how irritating Jim Malis is to listen to. I mean, it's like, I hope this helps you guys out. I can do these a lot faster, but I'd rather take some time, and sometimes repeat. I forgive the repetition, but I think I'm really a strong advocate. Повторение matučenia. Repetition is the mother of learning. It's good to hear this stuff. Hear it, because sometimes you miss it the first time. I know I do. But that's me, man. It might not be other people. But I oftentimes I miss stuff the first time that it gets said. So it's good to get emphasized sometimes. I hope this works out for you guys. The goal is for it to help you out. All right. Let's do 59, and that will take us through this whole thing. All right, guys. Finish the whole thing out with 59 for today for chapter 7. Problem number 59. Problem number 59. Many science fiction spacecraft are shown with cylindrical modules that rotate to provide the crew with artificial gravity. A centripetal acceleration that is comparable to the gravitational acceleration on the Earth, 9.81 meters per second. If one such module is 500 meters in diameter, a lot of times when they say diameter, they're trying to throw you off. Diameter is 2 times the radius. A lot of the formulas involve only radius. You can make it involve diameter, but what is the radius in relation to the diameter? R equals d over 2. The radius equals the diameter divided by 2. So just watch out. I've gotten into trouble with this one on occasion myself, doing them. If one such module is 500 meters in diameter, what is the speed of rotation that would provide an artificial gravity equal to that on Earth's surface? Report your answer to 2 significant figures in revolutions per minute and radians per second. Let's figure this out. You want the g that we're used to seeing to be equal to the centripetal acceleration. You want g to be equal to v squared over r, which is the same as v is omega r. Omega r, v is omega r, so v squared is the quantity omega r squared over r. This is it. This is where you want to go. Got to be careful. In the most natural sense, the radian rules the day. We know that. We can convert radians to degrees. We can convert them to revolutions. I think we'll be okay. Solve for omega. I'll tell you what I'm going to do. I'll solve for omega squared first. Let me divide by r first. Let me divide by r squared. Let me divide by r and I solve for omega. Let me divide by r. Let me divide by r on each side and I get omega squared. Let me square root each side. Omega equals the square root of the quantity g over r. Be careful, be careful. D is 500 meters. R is d divided by 2. 250 meters. Let's not get burned. Let's not get burned. Let's keep that in our mind. So, let's see what we got here, guys. We got this. Forgive me here. What are you going to say? Look, this is, let me use the white chalk. It might be a little more visible for you. I'm not in the bind for chalk right now, so I should be okay. This is 9.8 or 9.81. What did I use? I don't even know. Yeah, I think we used 9.81. The radius is 250. Stay with what they're going. That's going to be omega. You're going to do this. 9.81 divided by 250. And we end up getting, again, the real natural one, guys, is the radian. Is the radian. Well, okay, well, I guess while I'm delivering that speech, that's one of the answers. Can you give me revolutions? Yeah. This isn't a different quantity, you guys. It's like me saying to you, I just gave you 40 quarters. Me giving you 40 quarters is the same as me giving you 10 $1 bills. It's the same as me giving you 2 $5 bills. It's the same as me giving you 1 $10 bill. The 40 quarters is $10. We're not changing the units here. I mean, we're not changing the quantity. This is 0.20 radians per second. And what is that in revolutions? Well, this is radians per second. They wanted revolutions per minute. Do you agree that one revolution is composed of 2 pi radians? Yeah, 2 pi radians to go all the way around, 360 degrees to go all the way around, which is the same as 2 pi radians to go all the way around, which is the same as one revolution. And every one of those 60 seconds is associated with a minute. It's good to me. Got 12 over 2 pi. That's 6 over pi. That's going to be 1.9. 1.9 revolutions every minute, and they'll be able to mimic gravity. 1.9 revolutions every minute, and they'll be able to mimic gravity. That is the same as saying 0.20 radians per second. 0.20 radians per second, 0.20 radians per second, and omega is 1.9 revolutions per minute. That's it. That'll be it, guys. Again, I mean, utilize these as you wish to utilize them. If you need to jump ahead a little bit, go ahead, jump ahead. Whenever you want to turn back, you can turn back. There's going to be enough notes there, just pencil and paper, old school stuff, that I'm fortunate enough to have Canvas at my disposal. I can put stuff on Canvas too. Just looking at how that stuff is solved, pencil and paper, it seems to help, seems to be more efficient sometimes for many people. But I also want you to have the option to look here in case it can help. Hopefully it can help you guys. Okay? Well, it's great seeing you guys. We will do Chapter 8 in the next video. Thank you much.